Uh, good afternoon, ladies and gentlemen, and welcome to the regularly online webinar from MetaMAT. Today, it's my pleasure to have Professor Bart Van Damme from Switzerland, and he will be talking about bending waves in quasiperiodic beams and plates.
Thank you, Muhammad. Actually, I'm not a professor. I will tell you why. So first, I will talk briefly about Empa, what we do, and especially about our activities in metamaterials. But then the main part of my talk is about wave phenomena in quasi and aperiodic structures, some of the work we have done in this field in 1D and 2D. So Empa is the Swiss Federal Research Facility for Material Science. Is a fairly large institute. It's scattered over 3 cities. The main campus is in Dübendorf. There's also one closer to Bern in Thun, and a campus in St. Gallen in the east of the country. We are located, when I say we, the Lab for Acoustics and Noise Control is located in Dübendorf, where we have quite large facilities. So if we look at the campus, our lab is in these 3 buildings, because as you all know, for acoustics in the audible range, you need large facilities. So we have quite a bit of experimental facilities here. Our activities are very broad. We're an acoustics lab with a fairly long history. And then, but we're not a university. So Empa is a research institute. That's why I'm not a professor. I'm working here as a scientist. So our lab for acoustics and noise control is split up in 3 groups. I work in the materials and systems group, and we have a lot of different activities going on. So we work a lot in structural dynamics, obviously, where railway superstructures are a large part of our portfolio. We do more fundamental research in the field of metamaterials, also granular materials. We have some projects going on about musical instruments. But a second large part of our group works in building acoustics. So here on the right, you see some of the experimental possibilities we can do here. So we can measure sound transmission in an accredited measurement suite. We can investigate tapping noise. So this is mainly done for industrial partners who need certificates, but we also use it for our research. This is a reverberant room for diffuse field sound absorption measurements. The colleagues do research in the field of lightweight construction, so we can build full-scale wooden dwellings in our labs. And then obviously we have some anechoic rooms, full anechoic, and this is an image of our semi-anechoic room. The colleagues of psychoacoustics also do listening tests, so we can do controlled listening tests in our Aura lab. All this is supported by both numerical modeling and experimental work. Given our fairly long history here in the lab, we're lucky to be able to do quite a bit of experiments in all acoustic fields, but this is obviously supported by a lot of numerical modeling as well. This is our group, well, almost all of our group. I will today talk about work of the colleagues that here are highlighted in red. Our group leader is Andrea Bergamini here on top, and then we have specialists in fairly all fields of acoustic materials, from vibrations to buildings to sound absorption. So a little bit of information about the general metamaterial work that we do here. So we do fundamental investigations in the field of periodic boundary conditions, but also doing model order reduction in order to speed up especially the direct wave propagation problem. So calculating the complex wave numbers starting from the frequency. There is a quite nice publication of Domenico, where he shows that you can define algorithms to decide which degrees of freedom you have to keep in your model in order to accurately predict the wave number as a function of frequency, so the full dispersion relationship. We also work sometimes with metamaterials that include fluid structure interaction. I'm not going to talk about these today. Like much fundamental work, we do quite a bit of work on beams and plates to grant us better understanding, but both from a modeling point of view and from an experimental point of view. Then we also try to bring metamaterials to applications. One of the examples from our past is panels with increased insulation values. This here is a phononic crystal window with periodic stiffeners. So it's a plexiglass plate. For the final setup, there was a second plexiglass. So we had a sandwich setup, but it's locally stiffened by these odd shapes that at the same time can be used as vibration isolators, but which also increase the sound insulation. There we go. If we look, for instance, at the vibrational properties of this plate, when we look at wave propagation at 0 degrees horizontally, 90 degrees, and 45 degrees, we see that band gaps occur. So sharp drop in vibration transmission along these directions that are obviously direction dependent because the distance between the stiffeners is different in these directions, but which in the end lead to an increased sound transmission loss. This is a typical sound transmission loss graph. It shows the efficiency of the sound insulation, where in low frequencies, everything is governed by the mass of the plate. At high frequencies, the insulation is governed by the damping of the plate. And especially there, if we have a band gap, which contributes to higher damping, we get an increased sound transmission loss, so an increased insulation value, which amounts to more or less 6 dB for this example. On a bit more fundamental level, we have that's not working this way. So switch this one off. Especially Andrea Bergamini has been working on waveguides, metamaterials that rely on inertia amplification. It means that the masses in our mass and spring chain here don't only move up and down, but we couple this up and down motion with a rotational motion due to these diagonal struts here. And because of this combination of translation and rotation, we can increase the perceived dynamic inertia of these disks and therefore reach low frequency band gaps. So if we look at an animation here, I'm going to switch off my camera because for one reason or another, it doesn't like to recognize it. Let me see. There, I will switch it back on later. So if we excite this phononic crystal from one side, we see that the energy gets, or the wave is attenuated extremely fast. Within one unit cell, the amplitude of this wave is reduced by a factor 10, basically. And then using this fairly compact setup, we can decouple, for instance, 2 panes of a double leaf wall or a double window, once again with the aim to reduce the sound transmission and to increase the insulation. One of the fun things that we noticed when using inertia amplification mechanisms. So inertia amplification means that whatever mass you are using in your structure, you can amplify the perceived mass either by coupling it to a rotation or couple it to an additional translation of an assisting mass here. We've noticed that if we excite these structures with higher amplitudes, that non-negligible nonlinear effects occur. This is mainly because of the geometric constraint, the kinematic constraints between the motion of the main mass and the motion of the assisting masses. So this relationship is nonlinear, which results in the end in a nonlinear equation of motion. In particular, in the damping term, so in this publication, the one that's shown here, I show that the damping is nonlinear, basically what you expect from drag, not what you expect from viscoelastic materials, and that the damping coefficient is a function of these inertia amplifying masses here in the edges. So this results in the end, whether it's a translational inertia amplification or a rotational one, the one that I showed before, this results in an amplitude-dependent resonance curve. So if we excite at low amplitudes, we get a black curve. If we increase the amplitude of excitation, the eigenfrequency shifts to the left due to increased damping, and we see that the resonance peak gets broader, gets wider, which is also a sign of this increased damping term. I also want to say a little word, because I will use it later for the actual main part of the talk, which measurement and evaluation methods we're using. Something we demonstrated on a very easy setup, periodic beam, which is very well described in literature. You can calculate it analytically. So beam with a periodic thickness profile, excited here on the left with a shaker measuring the force, and then we scan the vibration velocity along the length of the beam with a scanning laser vibrometer. Typical length scale, so around 2 centimeters for the thick and the thin parts, thickness of 1 centimeter to 3 millimeters. And this leads to band gaps in the audible range, which in our lab is the main focus, and for which we have the experimental tools. So if we do the measurement of this one, we can clearly see the effectiveness of the band gap. So we see a very quick attenuation of the wave amplitude. And then one way to visualize the dispersion relationship in this beam is to calculate a two-dimensional FFT, so an FFT in the time domain, but also in the spatial domain, which gives us a frequency wave number map. As we can see, it agrees really well with the analytical calculations, which are shown here in white. Normally, the analytical calculations are only done in the first Brillouin zone here for low wave numbers. In reality, we see that past the first band gap, the main part of the energy is located in the second Brillouin zone. And if you would measure beyond the second band gap, most of the energy is in the third Brillouin zone. So this is fairly straightforward. So we get a good agreement between theory and experiment. The main problem here is that we have a fairly rude discretization in the wave number domain, which is based on the length of the sample we can measure. And it only gives us information about the real part of the wave number. So somewhat more interesting evaluation method is called the inhomogeneous wave correlation method, where you take the vibration pattern at a certain frequency f0, and you compare it to a theoretical damped propagating wave given by this formula. And then by calculating the correlation, we try to optimize, we try to find the maximum of this correlation function to see where the wave number is located. The nice thing is, in this case, we can optimize not only for the real part, but also for the imaginary part, G of the wave number. So if we're outside of a band gap, we see that the maximum of this correlation function is on the real axis. So the imaginary part of the wave number is 0. If we are measuring inside a band gap, we see that the maximum of the correlation is located in the complex plane, and that we have a non-zero component of the wave number. So if we do this once again on the periodic beam, we see a very nice agreement between theory and experiment. So the theory is the red line here. But we can also extract the imaginary part of the wave number. Once again, the agreement between experiment and model is remarkably good. Obviously, for the simple case of a 1D waveguide, in 2D, everything becomes a bit more complex, but it's feasible. So before going to our own work, I want to give a short introduction to what not only us, but other groups have been doing in the field of non-periodic metamaterials. One of the applications of non-periodic structures is wave localization. So in phononic crystals, where the band gaps typically come from the periodicity of the structure, you can change this periodicity by adding a defect locally, or by, as I'm showing in this example here, a fairly recent example from Danny Torrent and Marty Sabaté. You can overlap two periodic patterns, rotate one with respect to the other, which also leads to a fully aperiodic, no, not fully aperiodic, but with a new structure with a much larger unit cell than the original one. And both these mechanisms, so local defects, overlapping patterns, can lead to wave localization, because locally you break the periodicity that is needed for band gaps. So with this overlapping structure, they showed really nice results where you create localized wave modes. Basically, the waves cannot travel through the bulk of the material, but energy gets trapped in certain positions. Another well-known and not so young anymore in terms of metamaterials, from 2016 already, example of non-periodic metamaterials are the graded metamaterials, where you, for instance, place resonators, shown here as the black beams, with different lengths onto a host structure. What's the reason to do this? Well, for resonant metamaterials, you typically don't need periodicity to achieve a band gap. The only thing you have to do is place the resonators closer than half a wavelength apart, and the band gap will occur anyways. The problem is that this band gap is fairly narrow, centrated around the resonance frequency of these identical resonators. So the idea of these meta wedges was to broaden the band gap by having a range of resonant frequencies, where you can either block waves traveling in this frequency range entirely. So if the wave is coming from the left here, this energy will be trapped completely in the resonators, or you can also use it for mode conversion. If the wave is coming from the right, these surface waves are transferred into bulk waves. The same has been done for acoustic waves as well. So this is an acoustic wave sound absorber based on Helmholtz resonators. So all these little blocks here are Helmholtz resonators with a certain neck here, and then a volume underneath that defines the resonant frequency. And then by making a rainbow of different frequencies within the resonator, they, Noé Jiménez and his colleagues, found a nice broadband absorption tool, which is much thinner than what you can do with typical porous media. An example of a project where I'm actually collaborating, this work done by Bao Zhao, who is a PhD student at ETH at the moment, is using these graded metamaterials for enhanced energy harvesting. So if you place a rainbow resonator array on top of a host beam that is excited with bending waves, He adds piezo materials on these resonating beams here on the sides. The nice thing is these resonators don't only stop or block the bending waves that are traveling through the beam, they also slow them down. And by slowing them down, you increase the time those waves interact with the resonators. And by this increased time, you can also increase the energy that is finally transferred into electrical energy using this piezoelectric interface circuit. And this is what he's showing in the bottom graph here. If you're looking at this particular beam here, if you take away all the other beams, so you take away the rainbow, you just have one resonator tuned at this particular frequency, you get a blue line. But when you embed exactly the same beam within the rainbow trapper, you see that the power is basically increased by a factor of 6, simply because, well, not simply, but mainly because the waves go slower and there is much time of pumping energy into the harvesting circuit. And this is quite nice and fairly recent work that was recently published here. Other examples of aperiodic metamaterials include guided waves on the edge of two periodic halves. So in this case, there is a periodic structure on top, a periodic structure on the bottom. Oh, the reference got lost. Marco is not going to be happy. This is work from Marco Mignacci, also already from a couple of years ago. And due to the topology of the top and the bottom halves, you can guide wave energy, in this case bending wave energy, but at fairly high frequencies, along this boundary. And the nice thing is without any scattering. So at these sharp corners here, none of the energy leaks into the bulk of the plane, but the energy really sticks to this interface. Now, for this kind of topologically protected wave modes, you really need a nice, very well-made design to call it protected. Otherwise, you might have leakage, you might have diffraction here in the corners. And then also work that is going on in our lab, work of Sander de Donker here, is not looking at metamaterials per se, but at placing resonators, mechanical resonators, at their ideal position in order to reduce vibration amplitudes. Here we're looking at a cantilever plate, so a plate that is able to vibrate freely is clamped here on the left side, which has a lot of eigenfrequencies that we see here in the transfer function in blue. On the top, it's calculations. The bottom graph is measurements. What we can do is place mechanical resonators, tuned mass dampers, to reduce the vibration of the entire plate. And what engineers know everywhere is that the placement of these resonators is extremely critical. The thing is, they might be closer than half a wavelength apart. And that means that these resonators are not independent anymore, but that they start interacting with each other. Now, if you place 3 resonators in this case, there is one here, there is one here, and there is one here, intuitively, meaning at the highest amplitudes of the plate, we see that the overall vibration reduction is not great. There are still some antinodes clearly visible close to the source and even in the bulk of the plate. What Sander did is derive or create an algorithm that optimizes the simultaneous placement of multiple resonators so that the overall vibration of the plate is reduced to the maximum. And here we see that this algorithm defines that there should be 1 resonator close to the source and 2 resonators almost next to each other here on the top of the plate, which reduces the overall vibration of the plate much more efficiently. One of the difficulties here, or maybe one of the surprising results, is that although these resonators are identical, if we look at this particular resonance peak, which is supposed to be damped, that we don't see one single dip, but that we see at least 2 dips occurring, which means that these resonators start to interact with each other, and there is a frequency splitting of these identical resonators. Good. Then, after this long introduction, I will now go to 2 examples that we developed in our lab. It started a bit as a hobby project, especially the 1D example, which was done as part of a master project already a couple of years ago. And then there is more recent work on 2D quasiperiodic structures. So what do we mean with quasiperiodicity as opposed to aperiodicity? Well, quasiperiodic structures, they don't have any translational periodicity as what we normally use in metamaterials, but we can see local symmetries visually that will also have effects on the wave propagation. So the main idea is that this aperiodicity, this global aperiodicity, is well defined by some pattern rule or other. One example is here by Rajkumar Pal 3 years ago, the group of Massimo Ruzzene, where they're using modulation of the phase of the placement of the resonators in a quasiperiodic pattern. You can also take the example of 2 graphene layers and tilt one layer with respect to the other. In the case of incommensurate angles, so if the tangent of the angle is an irrational number, then in the end you end up with quasiperiodic, aperiodic globally, but quasiperiodic patterns. And a well-known example in 2 dimensions, this is the example I will talk about later, is the so-called Penrose tiling, where you fill a plane not with one shape. So with one shape, you only have the choice between triangles, rectangles, or hexagons. But Penrose showed that you can fill the plane in other ways using 2 or 3 different shapes. But if you do this, you end up with an aperiodic tessellation. So once again, locally, you can see symmetries, like you can find these circular, more or less circular substructures. But if you look closely, none of these is exactly the same, and none of these can be mapped by a simple translation from one to the other. So if we talk about 2 sets of scatterers, like these overlapping graphene layers here, we can think of beams that have 2 sets of thickness variations. Both sets are periodic, but when we overlap them, they become quasiperiodic. But we can do the same thing with spring supports, masses, or resonators. I will give an example of a beam with 2 sets of thickness variations and show what kind of effects this has. So this is a setup. We have this beam here, periodic thickness variation with period A on the top and with period B on the bottom. If A and B are identical, the ratio between these two, so A over B I call R, leads to a perfectly periodic beam, just the one exactly the same as the one I showed before. But then if we play around with this ratio, then we get 2 fairly different types of waveguides, as I will show. If R is close to 1 or close to a nice fracture, like 3/2, for instance, we get an aperiodicity that changes fairly slowly. In my paper here, I call it an adiabatic change. So if you look here at the left, it seems as if this beam starts being periodic, but then if you go further and further away, the phases between these 2 periodicities get farther away, and you still get some kind of periodicity, but with a different structure. So here we have also an almost periodic part, but with a thick section on top and on the bottom that are completely out of phase. And then if you take a ratio that is far away from any nice rational number, then you get beams that change very quickly. You really cannot recognize any kind of unit cell within the length of this beam. So what happens? What we did is an explicit analysis of the full beam. Since it's not periodic and there is no master unit cell visible within the length of the sample, we cannot do any kind of periodic boundary condition approach. So we made a full explicit 3D model of the beams. It's a beam, so you don't need that many degrees of freedom. And we did the same thing experimentally. So we calculate an approximation of the dispersion relation. It's not really dispersion because we're looking at finite samples using a spatial or a two-dimensional Fourier transform, as I showed before. And this is what we get. So for the periodic case, we get exactly the same dispersion relationship as what I've shown before. So we have a guided wave, then a large band gap, another guided wave in the second Brillouin zone, etc., etc. So we can measure up to 15 kilohertz, more or less, to get the idea. This is the experimental result. So we see a really good agreement between the numerical and the experimental part. What we also see is there is some energy leakage in the band gaps to other wave modes. If the energy cannot propagate as a bending wave in this direction, it tries to propagate in another way. This here is a dispersion relationship of bending waves in the out of plane direction, according to this graph here. So there is still some wave propagation visible, but in this noisy area, you clearly see the presence of a band gap. Obviously, the band gaps occur at edges of the Brillouin zone. So we go a step further. We have a look at the first aperiodic beam, the adiabatic beam, where on the right side, we have the almost periodic case with aligned thick sections. And here on the left side, we have an almost periodic case with out of phase thick sections. The nice thing is, if we excite this beam from the left and the right, we get a completely different image of the calculated dispersion curve approximation. If we excite from the right, the first thing the wave feels is this periodic beam with a very strong band gap here starting at 4 kilohertz. And this shows, so we see a propagating wave and then this noisy image that we recognize from band gaps. So waves have difficulty in propagating already at low frequencies from the right to the left. On the other hand, if we look at the unit cell that we could extract from this left side here, the first band gap only occurs at much higher frequencies. So we see a completely different image. The main image of the dispersion relationship is the same, but we don't get a strong band gap view as when we excite from the right. So basically the input, the mechanical impedance of this beam is very different on the left and the right, although it's the same structure. For this periodicity here, this is the edge of the Brillouin zone. So let's have a look what happens close there. Well, what we can deduce from this dispersion relationship is that we do see discrete frequencies where we seem to have a clear dot of propagating energy. Now, these are localized wave modes that are not induced by a local defect, but which is really an effect of the structure of the beam. So if we excite from the right, some of the energy leaks through this band gap area here, and then builds up to a localized wave mode in the left part, where it is allowed to propagate still because you didn't yet reach the band gap. So you see at 5,700, that's the first, the second arrow here, we get this localized wave mode. At 7,300, we get this localized mode. 8,000, we get this localized mode. So you see here, the wave is not allowed to propagate, but you can pump enough energy into the left side of the beam to reach a localized mode there. And at 9,100, we get this one. Localized modes, localized waves, we know exist in aperiodic materials. So that was not too surprising. It's nice that we see we can pump energy to the other edge of the beam, but it's not entirely surprising. A bit more interesting, I think, happens in the aperiodic beam with a very incommensurate ratio of periodicities. So the short period here is 50 millimeters. If we calculate, so this is a simulation, this is the experimental work. If we calculate the dispersion relation here, we see that there is a clear band gap here at 5,000 hertz. There seems to be a band gap here starting at 11,000 hertz, although there is a splitting of the wave number levels. But we also see horizontal parts with band gap behavior at lower frequencies already. Why is this? Well, if we once again look at the edges of the Brillouin zones, first of the two periodicities, so for A and for B, sorry, the longest period here is 52 millimeters, the shortest is around 3 centimeters. So this is the band gap that agrees with the long period, this with the short period. And where we see the other horizontal parts, those are basically linear combinations of these wave numbers. So the difference between the two gives rise to the first low frequency band gap, and then we get all kinds of linear combinations, resulting in fairly efficient band gaps, but at lower frequencies. Why is this? The reason for this I'm showing here. So here you see the efficiency of the band gaps, the imaginary part of the wave number in red. So we see at low frequency here, then we have the big band gap because of the longest period and the big band gap because of the shortest period. But all in all, these interaction band gaps don't seem to be very bad. Where do they come from? Well, we're talking about bending waves, and the bending stiffness of a beam is a function of the thickness squared. So we basically have to look at the reciprocal space of the bending stiffness of the thickness squared. And if we look at the Fourier transform of this thickness of the beam squared, we see high peaks at the edges of the Brillouin zone, here and here, but we also see high peaks at their linear combinations due to the interaction, the nonlinear interaction between these two wave numbers. So everywhere where you get a high peak in the reciprocal space of the thickness of the beam squared, you also get an interaction band gap, which is clearly noticeable and measurable. The advantage of this is that we get a band gap at the same frequency as in the periodic counterpart, but the bending stiffness of this aperiodic beam here is 5 times higher, because you almost never have thin sections at exactly the same place. So here there is one, but mostly you have at least one thick side on both sides of the beam. So this is about the beams. Now we go to plates. And once again, Massimo Rozzeni, but also Danny Torrent have done a bit of work in aperiodic plates and quasiperiodic plates in the recent past, the last 2-3 years or so. And all this work is going in the direction of wave localization, wave guiding, band gaps in these structures. These two-dimensional quasicrystals, what's nice about them is that when you look once again at the reciprocal space, you get symmetries that are not known from fully periodic crystals. So you can have 8, 10, and 12-fold symmetries in the reciprocal space. And this is basically the idea of this work here from this year. They start from 10-fold symmetry in this case. they calculate the inverse Fourier transform of this one to go back to real space. And based on these phase diagrams, they create thick and thin parts within a plate, which result in something that is globally aperiodic. And then if you look at dispersion in these kind of setups, you see that in some frequency ranges, so the frequency is on the vertical axis, and then you have kx and ky here in the horizontal plane. You see frequency bands with almost isotropic wave propagation properties, and then also frequency bands where you get direction-dependent band gaps. So in this direction, the wave can propagate. In this direction, the wave cannot propagate. You see a cut of these sections here. Once again, obviously with tenfold symmetry, because this is what you started from. We've done something similar, but yet completely different. We didn't start from a nice symmetry in the reciprocal space. Oh, I'll have to speed up a tiny bit to end within my 50 minutes. But we started with an existing quasi-periodic pattern in the plane. So this Penrose tiling that I showed before. And this is work that was done by Domenico Tallarico. This Penrose tiling, the P3 tiling, is based on two rhombi, a thin and a thick one. And there is an algorithm to make this puzzle. So you basically have to connect the squares and the dots. And if you do this, you can make a nice tessellation of the plane, which doesn't have any translational symmetry. This work is already available on arXiv. It's now in revision. And what we do is we will make a plate like this, not with thick and thin sections, but with scatterers that we place in the center of these triangles that build up the Penrose tessellation. If we do this, you get a structure that looks like this. So all the blue dots are scatterers, could be masses, could be resonators. I will show you what we used exactly on the next slide. We excite this plate here in this corner, and we look at the response here in this rectangle. Now, if we look at the reciprocal space of this Penrose tiling, we once again see a tenfold symmetry, but not with unique dots like in the work of that I've shown before, but with a much more complicated reciprocal space. We compare this Penrose tiling now with an hexagonal periodic counterpart, but with the same number of scatterers per surface. So that we really have something to compare, the same mass density, the same number of scatterers. But instead of having this complicated black reciprocal space, the hexagonal periodic space leads to these the sixfold symmetry with only one point in the middle, the gamma point, and then 6 points around it, shown here by G1. Now, what's the difference between the two? The first effect, or the first effect we would like to show, is gotten from multiple scattering analysis. It's an analytical approach where you can talk about wave propagation in infinite planes, and these plane waves meet the scatterers we put in their way. So if we look at the hexagonal pattern in red, the honeycomb pattern, we see a very deep band gap here at the high symmetry point G1. There is a second band gap here at low frequencies, but as I will show in the next couple of slides, this is not a full band gap. It's only valid in one single direction. And if we look at the Penrose plate in black, we see that smaller but clearly visible band gaps arise at high symmetry points. For instance, the K1 point here, the K2 point on the second circle here, and the K3 point just here at 10 kilohertz, which is a still higher wave number. So the high symmetry points seem to result in band gaps as well. We looked at experiments to do this. So it's quite a work. We have more than 600 scatterers on this plate here, which is more or less 60 centimeters inside. the scatterers themselves are small sticks sticking out of the plate, as you can see here. So they stick out from both sides. One of the first conclusions we drew was these are not point masses. And Domenico actually compared for the hexagonal case what happens if you use point masses, so the mass really located at the white points here, or if you use finite size studs that stick out of the plate, and you see a completely different dispersion diagram. So where for the point masses, the first band gap only occurs at 8 kilohertz, for the studs, you get band gaps that occur already at 4 kilohertz, mainly because the rotational inertia of these studs once again increases the perceived inertia of these scatterers. Here you can also see the reason why we saw this local band gap before. It's, if I'm not mistaken, in this area here, where there is a band gap in the gamma M direction, but not in the MK and not in the gamma K direction. If we do the experimental analysis of this Penrose plate, we see that at low frequencies, we get a more or less horizontal response. And here at 3 kilohertz, the response starts going down clearly, a factor of first 10, then almost 100 lower than the initial amplitude, which is a fairly good band gap. And Domenico shows in his paper that this can be related to a number called the inverse participation ratio, which is a measure of the modal activity, if you want, in this plate. Now, where does this come from? If we go back to the geometry of this plate, so if we see a high IPR, inverse participation ratio, we see a low transfer function and vice versa. So if we go back to the geometry of the plate, we see areas with a high density of scatterers, and then these open areas with a low density of scatterers. And this is where all this comes from. So the high density of scatterers looks like a phononic crystal with studs that are quite close to each other, closer than in the hexagonal counterpart. So they achieve a band gap at a fairly low frequency. In the open sections, you can create localized wave modes. And there we see a really nice agreement between the experimental work and the numerical work here. So basically, these scatterers that surround these open areas act as fixed boundary conditions, and the membrane in between can get its mode shape. So in this case, we see dipolar mode shape in this open section. Here we also get dipoles, but neatly arranged on this circle. So we show that overall there is band gap behavior, so the transmission is significantly reduced, but locally we get energy accumulation once more. So to finish my talk, very briefly, we have investigated band gaps and localized modes in some quasiperiodic beams and plates. We show that even if no supercell is present within the boundaries of our experimental cases, we can still reach low frequency band gaps, either because of interaction between the periodicities like in the beam, or because the scatterers become closer together at certain locations, and they lead to low frequency band gaps. And we get different mechanical impedances, which leads to an asymmetric vibration profile. What we're working on is boundary-dependent dynamics, as I would like to call them. So we can basically choose where low vibration levels are going to occur. So if these positions are critical for high vibration levels, we can create structures that don't vibrate there. Or we can play further with these interacting resonance scatterers, as I showed in the case of very few resonators, to get more of resonance splitting and therefore a wider range of effect. So with this, I would once again like to thank all my colleagues here. And if there are any questions, I would be happy to answer them.
Thank you very much, Bart. So now we have time for questions. So people just unmute yourself and ask if you have any. If unfortunately, if you don't have a microphone, you can eventually write inside of the chat your question and I can just read it. So don't be shy.
Bogdan is waving his hand.
I think Bogdan probably he just wanted to say congratulations for the talk.
Okay.